Now let us see what is isotope effect. As we all know, the isotopes are the atoms are of same element which have same atomic number and different atomic mass. So we'll see how it is related to the critical temperature, whereas the critical temperature is inversely proportional to the root of m, which is m is the atomic mass or isotopic mass. If we give an example of isotopes of a particular, as I said, isotope, an atom element will be the same, but the atoms will be different. Isotopes of the mercury. If we take the isotopes of the mercury, one of the isotope of the mercury will be 199 Hg and 200 Hg and 201 Hg. Whereas the critical temperature, if we plot in Kelvin, we have for 199 Hg we'll have 4.2 Kelvin, and for 200 Hg we have 4.18 Kelvin, and we have this much Kelvin. For 201 Hg we have 4.14 Kelvin. Okay. Now the variation of the critical temperature with respect to the isotopic mass or atomic mass, which is inversely proportional to the root of atomic mass. I mean, the entire formula is being put into the sentence formation. It means to say the critical temperature is inversely proportional to the root of the atomic mass. This is called as the isotopic effect on the superconductors. Now let us see the Meissner's effect. The Meissner's effect is all about the external field. That is, now let us consider a conductor here, wherein which a conductor is an element which allows all the magnetic flux lines. Okay, see, this is a normal conductor. It allows all the magnetic flux lines, and the flux lines are moving upwards. Here the temperature T is greater than Tc, the critical temperature. And here H is the field strength. It allows all the magnetic flux lines. And now we'll see a superconductor. The superconductor is a conductor wherein which inside the conductor the flux lines are moving downwards, whereas the flux lines outside the conductors are moving upwards. As you can see, the arrow mark is towards upwards outside, and the arrow mark is towards inside. Inside here we have the diamagnetic. This is called diamagnetism. And here the temperature is T lesser than Tc. Now we'll see what is diamagnetism and what is diamagnetic materials. After cooling, the resistance decreases and rho decreases. So it starts expelling all the flux lines, all the magnetic lines. So it is called as a superconductor. As after cooling, the resistance decreases, so the resistivity decreases. It starts expelling all the magnetic flux lines outside, and that's why they are called as superconductivity, because there will be induced current in the opposite direction, so they'll get cancelled out, and this is known as diamagnetism. And these kind of materials, the materials which exhibit diamagnetism is called as diamagnetic material. So now from this conclusion we can say that all the superconductors are diamagnetic materials, but not the converse. All the superconductors can be diamagnetic materials, but not all the diamagnetic materials are superconductors. Okay, so now let us conclude a statement wherein which a normal conductor kept in a magnetic field expels the magnetic flux lines completely when it is cooled below its critical temperature and hence becomes the diamagnetic material. Okay, I hope the isotope effect, the Meissner's effect, and the statement where the superconductors can be diamagnetic but not the converse, and a normal conductor which is kept in a magnetic field expels the magnetic flux lines completely when it is cooled and its critical temperature, and it's known as diamagnetic material, is clear. That's all for this video. Pen down. Thank you.